This is Harshavardhan Reddy, and today I am excited to present my project on finite element analysis of damage detection and repair quality assessment of high performance concrete using PZT sensors and MATLAB simulation. This project combines experimental testing, smart sensor technology, and numerical modeling to demonstrate how we can detect structural damage early and assess repair effectiveness in concrete beams using a cutting-edge non-destructive method called EMI technique, which is abbreviated as electromechanical impedance. Before going into the project details, let me give you a brief background of it. In civil engineering, structural health monitoring is critical for safety, reliability, and longevity of structures. Traditional inspection methods are often time-consuming and unable to detect micro-level internal damage. That's where smart sensing comes into play. Piezoelectric sensors offer a promising solution due to their ability to detect local changes in structural stiffness via electrical signals. In this study, I used EMI technique, which involves monitoring conductance signature across different stages of the structure, which are healthy stage, damaged state, and also post repairing retrofitted stage, using PZT sensors, which are surface mounted on a high performance concrete beam. Now let me explain the experimental setup which I have considered for this project. I prepared a prism specimen of size 150 by 150 by 300 mm from a precast HPC beam. The PZT patch was bounded 75 mm off the center line, and EMI responses were measured in 3 stages, which I mentioned already. The repaired specimen was cured in 3% calcium hydroxide solution for 7 days, and then the impedance reading were again recorded. We extracted conductance and susceptance values over the frequency range to analyze structural changes across each condition. Now, as the experimental setup was done, I tried to implement a numerical analysis for the same experimental setup using FEM analysis in MATLAB. To replicate and validate the experimental data, I developed a 1D finite element model in MATLAB. The beam was discretized into 50 elements, and the central node represents the PZT sensor. The material properties like Young's modulus, density, and cross-section area were assigned according to the material which was used in the experiment. Damage was simulated by reducing stiffness by 70%, and the repaired state was modeled by increasing stiffness by 30%. The Rayleigh damping models were used with tuned alpha and beta values. Using the frequency sweep from 30 kHz to 400 kHz with a time step of 100 kHz, I calculated the electromechanical impedance particularly particularly the conductance and the susceptance. As the numerical analysis was done, there were a bit errors which were optimized using optimization techniques in the MATLAB. Using MATLAB in square curve fitting method, linear square curve fitting method optimized the numerical results to match the experimental values. To evaluate the model's accuracy, I needed the root mean square deviation metrics, which were assigned accordingly. These values shown These values show significant deviation when damage and clear coverage were repaired, validating both the sensor sensitivity and repair effectiveness. From this experiment, my key observations were: the experimental and numerical conductance versus frequency plot showed similar trend. Damage caused a drop in conductance peak, indicating stiffness loss. Post repair, the curve shifted back towards the baseline, indicating partial stiffness recovery. The MATLAB simulation strongly correlated with physical observations, providing the model's reliability. So now I wanted to conclude that I successfully demonstrated how PZT sensor EMI technique and finite element modeling can be integrated for structural health monitoring of concrete. The approach is accurate, efficient, and has real-world potential for life cycle management of bridges, buildings, and other concrete structures. The MATLAB simulation not only replicates the real behavior, but also offer a predictive tools for early intervention planning. Now, I'd like to thank my faculty guide, Dr. Vishalakshi ma'am, and my uh, Department of Civil Engineering in Mahindra University. And I would also like to thank Ramesh sir, PhD scholar, for supporting me. Thank you for all your attention. I now be